Hi, Deborah and Tiara.
Hello.
Yeah. How are y'all doing?
Pretty good. How are you?
I'm good. Is business busy at the drugstore?
Not as much as it used to be when it first started. It was really crazy, but
Yeah. Okay. Well, yeah. I went yesterday to the drugstore to get my stuff, and there was nobody there. I was like, fine, I don't have to stand within 6 feet of anybody, and they've got a shield up. So, and I was wearing a mask. I'm not usually paranoid about things, but this one has got me.
yeah.
Hey, Tiara.
Hello.
You look happy today. I like to see that.
You like my mini stapler?
Oh, it's a pretty color. It's a pretty stapler. Yeah.
I know. Thank you.
Could you put it in a bag and mail it to me? Because I'm having trouble keeping all my papers sorted out.
No, I really need this. I'm sorry.
All right. I'll get my own. But when I try to staple my things, I can't find my stapler, and when I find my stapler, my stuff is all messed up. So whatever. Anyway.
I had to go buy one.
Yeah. Oh, and Alexis just walked out of view. I think she's coming back. She's coming back.
Yeah, my computer was acting up, so I don't know if it's gonna like disconnect. So I have to charge my phone so that I can be on Zoom.
Okay, we'll see. We'll hope you stay on. Guys, we didn't have much homework yesterday, but I found an error that it wasn't exactly an error, but something that looked like I said was equal and it wasn't in the last problem I did yesterday on the telescoping series. I really want to do that one again. So I want to start where we left off. All right, so let me share the screen. Hopefully Dion will be here in a brief minute. So let me get this going. And let's see what we got here. Okay. Okay, good. All right. So we really only had several problems last night to do, and they all had to do with this telescoping series thing, and that's not it. It's right down here. And I wanted to show you something I did. I didn't like what I did. I didn't like the way I did this. So we're going to look at it again, okay? And then we're going to go on from there and try to finish the rest of this section. And if we finish it, fine. If we don't, fine. But it's a really important section to the rest of the chapter. So that's why I want to make sure I get everything done right and you guys understand what I'm doing. I'm going to look at this sequence right here. And this is the end of your notes yesterday. So it's the sum from n equal 1 to infinity. Back up here. It's the sum from n equal 1 to infinity of 1 over n times n plus 1. Okay? And if I let me double check something on that. So that's the one we were looking at. And if I looked at some of the partial sums, they'd look like this. Or in particular, if I just wrote out some things. If I start at 1, this will be 1 over 1 times 2, 2 over 2 times, no, not 2, sorry. Let's fix that. 1 over 2 times 3, plus 1 over 3 times 4. And I think that's Dion ringing the doorbell there. Hang on just a second and let me get her in. Okay, she's coming in. Let me make sure she gets in here. Not quite there yet. I'll just hold up for just a minute. There you are. Okay. Oh, good. Dion and me match today. Y'all want me to teach like this?
Yeah.
I can't see with the hood on. I have to take it down, okay? All right. So, Dion, we're starting on a problem that I did yesterday, and we're going to go from there. I'm going to redo something, okay? So we've got, this will be 1 over 4 times 5. And the problem was this series right here. And we wanted to know if it converged. Now let's talk about, if it converged. And what the sum is if it converges. What is this thing getting closer and closer to? We said yesterday that if we want to talk about whether a series converges, we look at the sequence of partial sums. All right, and what that meant essentially was, if I looked at S1, it'd be 1 over 1 times 2. If I looked at S2, it would be the first two terms, 1 times 2 plus 1 over 2 times 3. If I looked at S3, it would look like 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. Oops. You get the idea here. I'm just adding things together and looking at that particular sequence. So this will be 1 over 3 times 4 and so on. So we're looking for the Sn, and we want to know if, as n goes to infinity, this sequence that just keeps on adding 1 every time has a limit, basically. So does the sequence of partial sums have a limit? Some of these problems are fairly easy to look at based on something called telescoping series. And what I wanted to show you, and I ran out of time yesterday, so I got myself in a hurry, and I shouldn't have. I'm going to change the color of my pen here. I had said that this could be written a different way. And the way we're going to write it a different way is to look at 1 over n times m plus 1. And that's the thing I'm trying to look at the sum of, okay, all of those things. Now, I said yesterday, and I said it real quickly, I was running out of time, but what I said yesterday was we can use a method we know on this that we used on partial fractions to write it a little differently. And remember, in partial fractions, what we did, if we were trying to integrate it, we would write a over n plus b over n plus 1, okay? And then if we multiplied through by n times n plus 1, we'd get 1 equal a times n plus 1, all right, plus b times n. All right, should be familiar to everybody. Everybody did great on partial fractions on the test, so we got what we need. So essentially then here, if we match coefficients here, guys, it looks like a is going to be equal to 1. Again, if I look at this I've got an an plus a bn. I just said something wrong. I just realized it. An plus bn would be a plus b times n. And there is no n term over here. It's essentially n times 0. So what we've got, we just break it up, is that n here, or a plus b, is equal to 0. So that's the first thing we're going to get out of that. A plus b has got to be 0. Now, the other thing is that this constant right here, a, has got to be 1, like it is on that side. So a has to be 1. And that tells me immediately that if you get a and b added together, and I know a's 1, b's got to be minus 1. Okay, so that's what that's what I'm going to do to split this thing up. So I'm going to look at this. I'm looking at the series, the sum as from n equal 1 to infinity of 1 over n times n plus 1. And that's the same thing as looking at the series from n equal 1 to infinity of 1 over n minus, my b's that, minus 1 over n plus 1. All right. So in other words, I use partial fractions to break it down into 2 pieces. And this caused something nice to happen here, or at least it caused something nice to happen that I can see. This is where I kind of jumped the gun yesterday. I didn't show you where I got that. I just kind of mumbled something about, okay, use partial fractions. But if I now try to write out the sum here, and let n be 1, I'll get 1. If I let 1 minus 1/2, that would be the first thing there. If I let n be 2, I get 1/2 minus, if I let it be 2 here, I get 1 over 3. So that's where, see, this is where n equal 1. That's the next one where n equal 2. where n equals 3, I get plus 1 over 3. So I'm plugging it into this thing right here, guys. Plus 1 over 3 minus 1 over 4. And you can kind of see what's happening here. The next one is going to be plus 1 over 4. Whoops, jumping the gun again. 1 over 4. All right. Minus 1 over 5. And it goes on until I get just, basically I get this 1 over n. The last one would be 1 over n minus 1 over n plus 1. I'm just putting my dots there and just say keep it going. That's what I would do. Now, the nice thing that I see here, that's Sn right there. That's the sum. That's all of these terms as they go infinitely on. And the nice thing that happens, because I split it up and use this partial fractions on it, is that we can see the following. We can see that if we group this and this, we get 0. This and this, we get 0. This and this, we get 0. Minus 1, the next one, guess what's going to be 1/5? That's minus 0. The one right before this one would be, notice that the negative one is right before the positive one, so that would have been that. That thing will drop out. And all I have left in the end is this thing right here that's 1 minus 1 over n plus 1. Okay, it collapsed. It's called a telescoping series. The problems you had to do last night were like this. And I don't know if you tried them, but just go ahead and try them again tonight. They work like this. Break them down using partial fractions and then let everything fall out in the middle. And what you've got is left is what's on the ends, the one here and that thing right there. We know that a series converges if the limit as n goes to infinity of this Sn, this total sum here, exists. Well, this is easy. It definitely exists. That's going to 0. This tells me that the sum of this thing is 1. Okay, the sum of this thing is 1. Everything collapses in the middle. This one goes down to negligible value. It's going to 0. I'm left with 1. So that we call that the sum of that series. Okay. Did anybody try the telescoping series last night? If you looked at them, if you didn't try it, that's just as well. Try it first tonight. Okay. Okay. So there, when we go through this chapter doing series, we're really going to be interested in whether if that limit exists, we say the series converges and that is the sum. So this is the sum, and we say the series converges. Now, I'm going to tell you that there are only a few series we can find the sum for. It's hard to find the sum, but there are tests we can use to test for convergence. So later on, if I ask you to find the sum of something, there are only going to be a few you can find the sum of. If I ask you to say whether something converges or diverges, the question is, what test do we have to figure that out? Okay, so hard to find the sum, easy to find out whether it converges or not. Not easy, but there are tests for it. Okay, so let's go on. Let's go to where I left off. So see what I was grouping. I did that. I did the same thing, but I crammed it all into the bottom, and I don't think I did it very well. Okay. All right, so let me give you an example of another one, whether it converges or diverges. I've got a series from n equal 1 to infinity of minus 1 to the n minus 1. So if I look at the partial sums here, S1, if I plug in 1, I get minus 1 to the 0. Anything to the 0 is 1. So the first term without adding anything to it is 1. The second thing in the sequence of partial sums, I go for 2 of them. So it's this one plus the next one. If I put in 2 here, I get minus 1 to the first. So there's that minus 1, I get 0. If I go for the next one, S3, if I put in the 1 and the minus 1 I got from S2, and then I put in a 3 here, that's an even number. Minus 1 squared is going to be 1. So I get 1. You don't have to look very long at this thing to see here that sequence of partial sums looks like this: 1, 0, 1, 0, 1, 0. When you start adding them up one at a time and adding 1 on every time, you get that. That thing does not exist. That limit, it oscillates. Remember, it's not getting closer and closer to anything. It just goes back and forth between 0 and 1. So what we say is that the limit of these partial sums, as n goes to infinity, does not exist. And when we get that, we say this series diverges. Okay, that series diverges. Okay. Now,
I have a question.
yeah.
Well, like, the thing ever start at like a different number other than 1?
Yes, they do. We'll look at a lot more series. They do start off with a different number other than 1. It's just the ones we've looked at lately all start off with a 1. Okay, we'll look at some more today. Okay, anybody else? Everybody okay with that? All right, let's look at another one. This one is interesting. This is a very special series, and what I get, it's got a funky little proof about what happens here. It's a little hard to see. Let me look at one other thing here, guys. Okay, there we go. It's a little hard to see, but here's my series. It's the sum from n equal 1 to infinity of 1 over n. Pretty easy. It did start out with 1, so this isn't a counterexample to what I just told Alexis. It's just another one that happens to start with 1. You know, if I put 2 over that, it would start with 2, for example. There's not much I need to do to change it, but this one's starting with 1. So the first term's 1. If I put in 2, I get a half, plus a third, plus a fourth, plus a fifth, plus a sixth, and so on. Let's look at the partial sums. S1 is 1. S2 is 1 plus a half. S3 is 1 plus a half plus a third. S4 is 1 plus a half plus a third plus a fourth. There's a reason I'm doing this, guys. I'm going to jump to S8. 1 plus a half plus a third plus a fourth plus a 5 plus a 6 plus a 7 plus an 8. Okay, that's S8. Now, what we did before, if you remember, one of the things we looked at early on with this stuff is that if I had something like a 0.6, 0.66, 0.666, you could tell that thing, we showed that it went to 2/3. I'm going to talk more about that one today, but the limit of that was 2/3. If I add up these fractions right here, it's going to be hard to tell. Sort of like the one I did yesterday where I added the fractions. I couldn't really tell, but there's a really slick trick in the book that talks about how you think about this. And the way I'm going to think about it is like this. If I look at S1, the S1 is 1, and that is clearly bigger than a half. Okay? Nobody going to argue with me about that. It's bigger than a half. If I look at S2, in other words, the first 2 added together, I get 1 plus a half, and that's bigger than 2 halves. Now, you might look at that and say, why is she writing it like that? Well, you'll see in a minute. But it's clearly bigger than 2 halves because 1 is bigger than a half. So I replaced that 1 with a half, and I said, okay, this is bigger than 2 times 1/2. That's the way I'm going to write it. All right. If we look at the next one, if we look at, I don't want to look at S3, but let's look at S4. All right, if I look at S4, this thing right here was bigger than a half. So 1 plus a half, 1 was bigger than a half. 1 plus a half was bigger than a half. If I look at S4 for a minute, I want to group those two right there together for a minute, right there. What's 1/3 plus a fourth, guys? Quick math. What's 1/3 plus 1/4?
7/12.
7/12, which is bigger than a half. Everybody agree with that? 1/3 is 4/12. 1/4 is 3/12. That's 7/12. That 7/12 is bigger than a half. There's another one that's bigger than a half. So when I look at this thing right here, move it up a little. When I look at this thing right here, Now this grouped term is bigger than a half. Well, that was bigger than a half. If I look at it, that was bigger than a half. The first two, that was bigger than a half. That's one half, that's 1, 2, 3 halves. So that's bigger than 3 1/2s. All right, that's bigger than 3 1/2s. Now, this pattern goes on, guys, and I want to talk to you about what happens here. The next one I'm going to look at is S8. Okay, when I look at S8, I do 1, 2, 3, 4, 5, 6, 7, 8 terms. That's bigger than half. That's a half. So 1 plus 1/2 bigger than 2 1/2s. That's bigger than a half. I'm not going to ask you to do this one in your head, but if you put that in your calculator and hit math frac, or if you wanted to find common denominators as a lovely little exercise, you'd find out that that's bigger than a half. So all of those things together now are bigger than 4 halves. They're bigger than 4 halves. You can show that this goes on, and essentially what happens is this. Notice the powers I looked at. I looked at 2 to the first, 2 to the first, I looked at S2. Well, I looked at 2 to the 0, that would be 1. 2 to the first, right here, I looked at S2. S4 is 2 squared. S8 was 2 cubed. And if you look at this, what comes out in the end is that if you look at the subscript that's the power here, and you look at what I ended up with on the ends, if this power is 2, there's halves in every one of them. If this power is 1, I get 2 here. If this power is 2, I get 3. If this power is 3, I get 4. If the power is k, I get k plus 1. That's the pattern. It's just 1 higher every time than this subscript. Now, here's the deal. So if you looked at S sub 2k, and that can get bigger and bigger, your sequence of partial sums, because 2 to a power, I'm just looking at every one, not all of them, but just sort of the ones in between here. That's bigger than k plus 1 to the 1/2. So if I looked at, for example, S32, S32 would be 2 to the 5th, 2 to the 5th. That thing's going to be better than 6 times 1, bigger than 6 times 1/2. The bottom line here, guys, is as far out as you go, this sequence of partial sums is going to be bigger than k plus 1 over a half. Now, what if I let k go to infinity, guys? What happens if k goes to infinity here? What does this do? Where's k plus 1 go? It goes to infinity too, doesn't it? Because adding 1 to infinity is still just infinity. And how about if I divide it by 2? So what? I take infinity, I divide it by 2, I still got infinity. This thing goes to infinity. In other words, the sequence of partial sums can be made as large as I want by doing this weird grouping here that shows I can make it infinitely big, okay? So if I can make it infinitely big, arbitrarily large, then the limit doesn't exist. It's just going off to infinity. So we say this sum, or this sequence of partial sums, which is the series, does not converge. Consequently, the series that it came from diverges. All right, this series has this is a very important series. It's called the harmonic series.
Like, is that like a type of notation or something?
Which one? This.
The little dots before the.
Oh, good question, Alexis. That's ... means therefore in math. That's my shorthand for therefore. Okay, that's not form, but for. Let's do that again. Therefore, okay, so it diverges. Therefore, or so it diverges, however you want to think about it. But that's notation, shorthand notation for therefore in mathematics. Okay, let's move a little further, and I've got a little more on this. It's a definition. It's so important that it's listed as a definition. The series, the sum from k equal 1 to n, and it really doesn't matter if you use k or n here, it's going to be the same series. It'll be 1 plus 1 over 2 and so on. It's called the harmonic series. It is divergent. I just showed that I can make it as big as I want. The sequence of partial sums does not reach a limit. Okay, you need to keep this one in your pocket, and whatever form you want to. We'll usually see it with n, guys. N equal 1 to infinity. I'm not sure why I switched over to k, but it doesn't really matter. It's the same series. But there it is. That thing diverges. We're going to be able to use that in a lot of ways that you can't quite foresee yet. Okay, so keep that one in your toolkit. Okay, next thing. There's another special type of series called a geometric series. And I bet, I don't know, some of you guys might have seen geometric series before. They have a really special form. And the form of a geometric series essentially looks like this. You start out with a number, and then you get the next number by doing what? What if I wanted to say, how did I get this next number? What did I do, guys, when I went from here to that term? How are they related? We multiplied by what?
R.
We multiplied by R. Look at going from that one to that one. You also multiplied by R. The next one's going to be AR cubed, and then AR to the fourth, and so on and so forth. So a geometric series, if A is not 0, you don't want A to be 0. A geometric series is one that essentially looks like this. The sum from n equal 1 to infinity of A R to the n minus 1 power. Now let's see if that's what that means. If n is 1, we'll get R to the 0, so the first term is A. If n is 2, we'll get AR to the first. If n is 3, we'll get AR squared, and so forth. Something that's in that form is called a geometric series. Now, you would want to look at the terms of the thing. So if I said, do you think these are geometric? I hadn't got it in a series yet because I hadn't added them together. But do you think you can get from one to the other one to the next one to the next one by starting somewhere and then every time by multiplying by something? Well, I kind of gave it away here because we started at 5. If we want to get to 5/10ths, we'll multiply by a 10th. If we want to get to 500ths, we'll multiply by a 10th and get 500ths. If we want to get to 5,000ths, we multiply by a 10th and we get 5,000ths. What that tells me is that thing is geometric because you can get from one term to the next term to the next term. Now, if I wanted to write it as a series, actually, I think I've done it down here. Let me just check. Yeah. So if I want to write it as a series, it'd be the sum from n equal 1 to infinity of 5, and then we have the 1/10 to the n minus 1. That's what it would look like. Okay. And you can see here that if n is 1, that'll be to the 0 power, so I get a 5, and then it'll be plus. If we do the series, then guys, what it ends up doing is it ends up adding all these things together. Okay. We already looked at one like this, actually. And the one we looked at was the one that had 0.6, 0.06, and 0.006 in it. And remember, if we added those things together and kept adding them, we'd have 0.6666, and that thing did have a limit. It went to 2/3. So if I look at what it looks like in series notation, it's going to look like the sum from n equal 1 to infinity of 0.6 1/10 to the n minus 1. Sometimes it's helpful to look at this and write out the terms so you can clearly see what's getting multiplied by what, to identify your A and your R. So in this one, my R is 0.6. I mean, so my A is 0.6. That's where I start. And to get to the next one, I multiply by a 10th because I want to move the decimal over one to the left. So those are all geometric series. Let's look at this one. This is a little different because if you look at that one, what you end up having is these alternating signs. We can kind of fix that. But if I look at it, I can get from this term to that term by multiplying by minus a half. And then if I multiply by minus a half again, I'll get to 1/4, positive 1/4. Minus a half again, I'll get to minus an eighth. So here's a case where when I keep multiplying by the thing that I'm going to identify as R is negative. So it starts changing the signs. So where I begin is 1. What I multiply by every time is minus a half. I'm going to write that as the sum from n equal 1 to infinity of 1 times minus 1/2 to the n minus 1. Okay, and that minus 1/2 is what is your R. It works out well. If n is 1, that'll just be a 1 here because that's to the 0 power. If it's 2, I'll get this thing to the first, so it'll be 1 times minus a half, and I'll get that. And again, if you're looking at the series, you're adding these things together. I just wanted you to see if you look at them beside each other, you can see what you need to multiply by 1 to get to the other one. Okay, question anybody. Geometric series is what can be, are nice. They're very nice. I can look at this. If I look at a geometric series and I know what R is, I can tell you whether it converges or not. And sometimes it converges and sometimes it doesn't. So we'll look at another one in a second. Okay, question anybody. This is just where I wrote everything out that I put up there. Okay. All right, now let's see if we can figure out where geometric series converge. If you let, this is my definition again, a geometric series, if you let A be non-zero, then the geometric series A plus AR squared and so on down the line, multiplying every previous term by R, number 1, converges if the absolute value of R is less than 1 and has sum A over 1 minus R. So not only does the R tell me if it converges or not, it plays a part in telling me what the sum of this thing is. Now, we have a great example for this already. Let me show you, let me back up here to get some blank space, and I'll show you what I mean here. This is good enough. This blank space will work right here. Let's go right in there. Remember how we had 0.6 plus 0.06 plus 0.006, and that one we just showed a second ago, 0.006, that was geometric with A equal to 0.6 and R. Do you remember what R was there? How do you get from this term to that term right there, guys?
1/10.
1/10. R is 1/10. Divide by 10, and it's so on. Now, what the sum that this theorem says, the sum of this thing is A 0.6 over 1 minus R, which is 1 minus 1/10 here. Okay, so what is 1 minus 1/10, guys? How many tenths is 1 minus 1/10?
9/10.
It's 9/10. Now, why? Who knows why I wrote it like? I don't want to write it like that. I want to write it as 0.9 because I think you'll see better what I'm doing. That's 0.9. If you reduce that fraction, move the decimal over in both cases, you get 2/3. We know that that's what that thing converges to. And notice that the R here, the absolute value of R, was less than 1. That's what we're going to look at to see whether the thing converges or diverges. And we're going to be able to tell what the sum is if we'll just identify A and R. It's A over 1 minus R. All right. Now let me prove that to you generically. I'm gonna do a proof of that theorem, guys. And listen, I want you to just listen to me. I don't want you to write this proof down. I want you to listen to me, and you can come back and look at it later and write it back down if you want to. But I just want you to understand what I'm saying as I go. 2 conclusions here. If the absolute value of R is less than 1, this thing converges. We just saw one that converged. We just saw how we found the sum. Now here it says, if it's bigger than or equal to 1, it diverges. So I'll give you an example of that. If I had the sum from n equal 1 to infinity of 5 to the nth, notice what that would look like if I wrote things out would be, if I let n be 1, I'd get 5. The next one would be 25. 5 cubed would be 125. It's definitely geometric, guys. What's A if I look at this? 5. And how do I get to every one after that? What do I multiply by? Well, I got 5, and 5 times 5 is 25, and 5 times 5 times 5 is 125. Not only is A 5, but R is also 5. What this is saying is, if R is 5, this thing's going to diverge, okay? And you can pretty much see that when you start adding the sequence of partial sums, looking at the sequence of partial sums, that looks like it's getting big. So here's what I'm going to do. I'm going to say, what if R is 1? Look at your series. And that would be like looking at this one right here. Suppose I had 1 right there. Then instead of a string of these 5s, that thing would be 1 plus 1 plus 1 plus 1 and so on, okay? If I look at the series here and put in R equal 1, it's just A plus A plus A, because 1 to any power is going to be 1. So every one of these turns out just to have an A in it. If you look at A plus A plus A, Sn, n of those, the nth partial sum is going to be n A's. I mean, A plus A would be 2 A's, A plus A plus A would be 3 A's. If I have n of them, I'm going to have n A's. If I look at the limit of that, and A is a constant, if n's going to infinity, this thing's going to infinity. That's pretty easy to see. It's like, what's the limit of 2x as x goes to infinity? Well, it's infinity. So that's why the equal one is in that. All right. So if it's equal to 1, it diverges. Likewise, but for a little different reason, if R is minus 1, it also diverges. Now look what happens if R is minus 1. Go up here to the geometric series. You get A. If R is minus 1, you get minus A. If R is minus 2, if R is minus 1 and I square it, I'll get plus A. If R is 1 and I get a cube, it's going to be minus A. What you see is that it does this A, minus A, plus A, minus A, plus A, minus A, on and on. And if I look at the sequence of partial sums, S1 is the first one, is 1. If you add the first 2, S2 will be 0. If you add the first 3, the first 2 together will be 0 plus A. And then if you add the next one, it's going to be 0 and so forth. Here's a sequence that oscillates. That thing diverges. That thing diverges. So if it's either 1 or minus 1, it diverges. And now, let me finish the proof here. Now, I'm going to prove to you that sum, that A over 1 minus R, works if R is, it'll give me a sum if the absolute value of R is less than 1. I'm going to do what I did yesterday. Do you remember yesterday when I said, how could I prove this 0.6666 and so on was 2/3? What I did was I let that be X and I multiplied by 10. And then I subtracted the 2. So I get 9x. And what happened is all the infinite stuff dropped out and I got 6 and I got X equal 2/3. That was a trick. This is the same trick here. So I'm going to show you how I got the generic formula for the sum. If I look at these two things right here, I'm going to let Sn be the nth partial sum going all the way up to AR to the n minus 1. Now, guys, the reason it's not going up to n is because you've already accounted for one of these things here. So that's the first one, second one, third one, fourth one. The end one is the n minus first one. And then I'm going to multiply by R. kind of like I multiplied by 10 in that other one I did. I'm going to multiply by r. So what it does is it bumps over every one of these one spot. So a times r is ar. A times ar is ar squared. Or r times ar is ar squared. R times ar squared is ar cubed. So the next one in there will be ar cubed, and so on. Then I'm going to do what I did again. I'm going to say, let's subtract these two things. Let's take Sn and subtract Rsn. I'm doing the same thing except I'm doing it generically. Remember how I've subtracted x from 10x here? I'm going to subtract Rsn from Sn here. Now, notice what happens when I subtract. Now, guys, I'm subtracting this one right here. All of these were right there. There's that one, there's that one. The next one would have been that one. When I subtract them, that whole middle collapses. It's like the infinite part of this dropping out. So the only thing that's left, and that one of them collapses with that, and the only thing that's left is the A. Again, I'm taking this away from that, is the A minus AR to the nth. Okay, because I was subtracting, all of these were negative. So that's why that minus AR to the nth. That was left, and that was left. So I've got Sn minus Rsn is A minus ARN. Pull out the Sn. Divide by 1 minus R. If I divide this by 1 minus R, it'll be A over 1 minus R. Minus AR to the nth over 1 minus R. Now if I look at the limit as n goes to infinity, guys, this thing is just a constant. It doesn't have any n's in it. So it's just A over n minus R. This thing right here, remember we did a little theorem back in 11.1 that said if R, the absolute value of R was less than 1, that this thing went to 0. That's what happens. And that limit ends up being A over 1 minus R. This is 1 minus R right there. So the sum Sn of a series, of a geometric series, is A over 1 minus R. Identify A, identify R, and you'll get the series. Okay. I'll give you some examples. Guys, mathematics, some of you guys might be mathematics majors, some of you might be chemistry majors, but at the very heart of mathematics is being able to prove something generically. Not just say, I can show this works for 50 different things. I need to prove it generically because maybe it goes false on the 51st one. It's very different from science. In science, you say, this is my hypothesis because this is what fits all my cases. In mathematics, and then maybe there's a bad case out there somewhere you hadn't come across, but in mathematics, I have to prove it for all cases, no matter what. In science, if you find a bad case or you find a different case from what your hypothesis says, you change your hypothesis, okay? You say, okay, in the light of this new evidence, I think this is how the universe began, or whatever the heck you're talking about.
Yeah, why are you
Okay.
smiling?
What's that?
You're just smiling.
You're smiling because I'm talking, well, I don't know, why are you smiling, Tira? Tell me why you're smiling. Have you heard that before?
Just really happy today, you know?
Okay, all right, she's happy. I don't know if it has anything to do with what I'm saying or not. So anyway, science and mathematics are a little different, okay? So I'm pretty much, Deborah, are you gonna major in mathematics or what are you majoring in?
I'm not sure. I'm considering it though.
Okay, good. You guys, Tierra and Alexis might minor in math, but you're probably basically science majors, right? Do you consider?
Yeah, I'm not majoring no math. I'm just gonna keep them in mind.
Okay, you're just taking the math because of the science, all right? Tierra, what are you doing?
I'm very undecided.
She's very undecided now. Okay, Dylan, what are you doing? She's down there. Is she asleep? No, she's looking up at me. Are you majoring in? What are you majoring in? Do you know?
She majored in math.
You gonna major in math? That's fine with me. So anyway, they're very different, but one complements the other. Actually, the most important one is mathematics because you can't ever do science without mathematics. So there you go. That's my opinion, and I'm sticking to it. Okay. All right. So I don't want that there. So let's go on and do a few examples. So let's see what I got here. So we sort of know what a geometric series looks like. I'm scrolling through this thing to see what I've got going here, guys. If I look at, there's another series, I'm sorry, I'm starting to stutter here. But there's another theorem that's very important to us. And that theorem says this. It says, if you're looking at a series, if a series sum an is convergent, then the limit of the nth term here, the limit of this thing right here, must go to 0. If it's convergent, that must go to 0. Okay? Now, if it doesn't go to 0, you can automatically say it diverges. This is why this thing often is called the nth term divergence theorem. So if it doesn't go to 0, it does not have a chance to converge. If it goes to 0, it has a chance, but it might not. Okay, so we'll talk more about that later, but here's the proof of that one. I'm going to run through this quickly, and we can come back and look at it later if we need to, but I want to look at some examples. The nth term, an of a series, is an equal Sn minus Sn minus 1. So if you want to look at, if you've got a whole bunch of terms here, and this is S5, and this is S4, S5 minus S4 is the last one. It's A5. That's all that says. Now, if S is the sum of the series, we know the limit as n goes to infinity of Sn is S. And also the limit as n goes to infinity of Sn minus 1 is S. It doesn't matter if you look at n terms, or 50 terms, or 80 terms, you're still, if you let n go to infinity, you're still going to get S. So that says the limit of this one minus that one, which is an, is 0. So that says if these things right here converge, then an, the limit of an, has to be 0. Now, again, we'll come back and look at that in a minute, but let me give you the test. The test says this, and then I'll give you an example, and we'll probably be talking about this again tomorrow. The nth term divergence test says this. If the limit as n goes to infinity of an is not 0, then the series diverges. If the limit as n goes to infinity of an is equal to 0, then further investigation is needed. In other words, if it goes to 0, it has a chance to converge, but it might not. I'll give you an example. This is a great example to remember, and we've already seen it. I just told you it was really important. This was the harmonic series. This is my an. The limit as n goes to infinity of 1 over n is what, guys?
0.
It's 0. This thing has a chance to converge, but we already showed earlier in the lecture that it doesn't. It doesn't, okay? So further investigation is needed for that. Let me show you another one. Suppose I said, let's look at the series n equal 1 to infinity of 2n squared plus 1 over n squared minus 1. There's an. What's the limit as n goes to infinity of an? 2n squared plus 1 over n squared minus 1, guys. What's that limit? Tell me what it is.
2.
2, exactly. It's like what we learned in Calc 1, right? Because of these things right here. That thing right there, this is what this is for. If that thing does not go to 0, which it doesn't, that is not 0, then this thing diverges. And we just proved it up there. I don't have to do a bazillion problems saying it diverges. We just proved it, that if that thing doesn't go to 0, this thing diverges. We will use that over and over and over again in the next week or two. All right, a couple of other quick things. These are theorems in the last part of the chapter. If an and bn are series such that aj is equal to bj for every j greater than k, where k is a positive integer, then both series converge or both diverge. In other words, what?
All these letters, J, K.
I know this is tough, and we'll come back. They're the last few theorems in the book, and I'm running out of time. But all it says is, I'll give it to you with an example. If the series look the same after a certain point, they're either both going to converge or they're both going to diverge. In other words, the first few terms in the series don't make much difference. So, for instance, in this one, if this is my K right here, and this is my J, for every J bigger than that K, these two series look alike. That's all I'm saying. If they look alike from some point on, they're either both going to converge or they're both going to diverge. This was the harmonic series, guys. We know that diverges. Then what do we know about this based on this theorem? It doesn't make much difference. It's still going to diverge. Okay. There's a proof of that in the book, but I'm going to have done with the proofs in a minute. Same thing here. Well, let me give you one more example today, and then I'll let you go, and then I'll come back and I'll start with this tomorrow. I don't want to rush these because they're important. Look at this one right here. That thing is a telescoping series. You guys can show that it converges. This thing, I contend, if I looked at this thing right here, if I let n be 1, I'd get 2/3. If I let n be 1, no, I get 2. Hang on. I get n is 2. The next one would be 2/3. If I let n be 3, I'd get 2/9. Then I get 2/27. What kind of series is that, guys? Look at that and tell me. We learned it today already. What kind of series is that?
That's the
Geometric.
Geometric. Tell me what A is. Tell me what A is.
2.
2. Tell me how you get from everyone to the next. I just did so. I shouldn't have done. I should have done it like this. Sorry, darn. You can't. I was going to say you'd have to multiply by 1/3, but that's going to mess up with the 2 there. I'm going to write this like this. 2/3 plus, let's do this. 2/3 to the nth times 3 to, you know what? I wish I had more time, but I'm not going to hold you. I know Deborah's got to go to work. And this is a convergent geometric series. I would probably do it like this. I would say 2, and then I'd write 1/3 to the n minus 1. Notice that the 2 will come out of that whole works right there. That would leave me with 1 plus 1/3 plus 1/9, and so on, 1/9. Now tell me what R is, and this 2 ain't going to make a difference here. If something converges, then a constant times it's going to converge. So what would the R be in this one?
1.
Well, the A is 1, and what's the R?
Oh, 1/3.
1/3. And remember when they converged? They converged when the absolute value of R was less than 1, and 1/3 is less than 1. If this one converges and that one converges, then the sum of the two converge. Okay? What I want you to do for homework tonight, do as many of the geometric series and the telescoping series as you can. There's some mixed series like these down there, but we'll come back tomorrow. I'll give you these theorems that I've got even a couple more of these theorems to do. But I'll give you these theorems in a nice compact number. Oh, well, another one says, if something converges and something diverges, then the two have to diverge. This one's going to converge. That is a geometric series, with the first number being 1/5 and R being 1/5. What kind of series is that? What's that called?
Harmonic.
That's harmonic. That one diverged. That one converges. If you got this one that diverges and one that converges, the divergent wins. It's going to diverge because it's not going to add up to anything. And no matter what you add up to it, it doesn't add up to anything. If it goes to infinity, this is not going to make any difference.
It's going to mess up my brain.
I'll come back and do some examples tomorrow, and I will shut up right now. I keep saying the same. I keep
What-
saying it over and over again.
What's this called? Rules? Like, what are these?
These are theorems in mathematics. When they are rules that I prove in general, and they're called theorems. And I'll have a better. Do as much homework as you can tonight. If you get stumped on one, it might be a good thing for us to look at it tomorrow, so I can bring these theorems out and show you why one works and one doesn't. Okay, so do as much as you can. I don't think there's anything due. Is there anything? Wait a minute. Is the sequence quiz due today?
No.
Tomorrow?
No.
I think that's maybe Friday.
Oh, Lord Jesus.
It doesn't have a due date on it.
Let's make it due Friday then.
Oh.
Okay? Let's make it due Friday. That's the sequence one. That one should be pretty easy. Okay? Go ahead and do that. Do some of this tonight. We'll do more of this tomorrow, and then we'll go on. But try to look at the sequence. See, we need to at least get it in by the end of the week. So let's do 5 o'clock on Friday. Okay? All right, I'll come back and look at these theorems tomorrow, and I'll see you tomorrow. Okay? Later.